I've been kind of playing around with empirical orthogonal functions, or EOF analysis. And, one example is this paper shown here that was published last year. I'm excited about it because it is, for a couple of reasons. One of them is that, EOF is sort of a model structure that's really kind of canonical and central to, physical oceanography and atmospheric sciences. And I think it has a lot of use for fisheries, but we have kind of community ecology has this sort of dust bunny distribution, a lot of zeros and then a few extreme values. And, people hadn't done a lot thinking about EOFs for ecological data because of that kind of non-normal data. So I think that there's a lot we can learn by having EOF analysis kind of set up for fisheries models. And then I think it specifically is sort of useful for kind of ecosystem synthesis and climate analysis to look at kind of dominant modes of variability. So I'll just kind of walk through this sort of case study where we tried to, do this sort of integrated, whole of ecosystem model, kind of soup to nuts ecosystem model. So we kind of kludged together 40 years of data for direct measurements of ocean physics, bottom temperature, and sea surface temperature, as well as hindcast and forecasted values from a downscaled Earth systems model using ROMs. We've got these size fractionated spring and fall chlorophyll A depth integrated samples, bottle samples. We've got secondary producers in terms of Calanus, 2 dominant Calanus, copepod species. We've got surface trawls for juvenile pollock. We've got bottom trawls, large mesh bottom trawls for the 5 species we looked at before. Or 5 species, slightly different set of 5 species. And we've got seabirds from the North Pacific Pelagic Seabird Database, and then catcher processor fishing effort. So sort of like, physics to people and protected species. And if you look across time, we've got this kind of block of data that we reliably get in the summer. We have kind of increasingly, during my predecessor Mike Sigler's time, there was this big push to get kind of ecosystem information in the fall to look at overwinter survival of commercial species. And there's also a lot of data for seabirds, kind of from observer, not observer, from kind of opportunistic seabird enthusiasts, in terms of sort of an, vertical and seasonal model here. We've got different data sets and different seasons, but it's, a pretty good kind of vertical seasonal spatial coverage. And again, in this case, I'm going to do, what I've been calling kind of dual ordination. So using the fact that there's an L matrix, a loadings matrix across time here and across species. So it's a way of generating covariance in all of the ecosystem components in their sort of spatial configuration. And I'm specifically doing this very simple sort of model for the covariance among categories. And I think there's 20 variables listed here, but there's only 18 processes. There's a bottom temperature direct measurement in the summer, and then there's a bottom temperature model, hindcast and forecast in a ROMS model, and the same thing for winter surface temperature from a satellite versus a ROMS model. And so in this case, I specify this kind of L matrix, this loadings matrix, such that I ensure that the bottom temperature direct measurement and the bottom temperature ROMS model have the same loading on a latent factor, epsilon. And so if you kind of just sit down with a pencil and paper, you can kind of work out that the difference between omegas in that case is what's called a delta change method by oceanographers. So it's kind of a statistical intercalibration that corrects for spatial bias in the ROMS model. So visualizing the output, across these different ecosystem components and looking at the omega term in the model, you know, bottom temperature looks like this, and this makes sense. This, you know, ice is produced at this ice, or below freezing temperatures are produced by this ice factory and kind of get advected southward in the middle domain. Sea surface temperatures get colder as you go north. You know, the difference between the bottom temperature and the bottom temperature ROMs is what is being soaked up as in the delta change method that's being estimated. Spring chlorophyll is produced off Jemchug Canyon. So this is the beginning of the Bering Sea Greenbelt, where, you know, nutrient-rich waters get advected out of this deep canyon. I think it's the broadest canyon of any shelf, although don't quote me on that. And that, you know, there's like, you know, myctophids that feed down there and then they get fed on by seabirds. So it's sort of one of the engines of productivity in the system that shows up in the data, both for small and large chlorophyll in the spring. By the fall, you know, it's been depleted after spring mixing, and then subsequent hotspots are kind of localized and based on sort of storm intensity. And so, you know, near the Pribilof Islands, maybe there's a larger mixing on average. Calanus in the spring is more south than it is in the fall. Aegzia pollock is everywhere. You know, adult pollock are concentrated in this kind of outer, you know, middle and outer domain. Cod, snow crab in the north, tanner crab, and, you know, anyway. So this, you know, the catcher processor in the spring is further south than in the fall, and we've got these distributions of fulmars and shearwaters. So that's sort of, you know, the SDM, kind of classic SDM distribution of these different ecosystem components. And then they're all being driven in this EOF model by by multiple factors, temporal indices. And in this case, I'm specifying two indices. The first one, after PCA rotation, is shown in this black line with a standard error shown in gray, and it's extremely highly correlated with the cold pool. And then we can forecast it forward, and we think that future years will look kind of warm, similar to recent past. So that's sort of what EOF is doing. Let's see, we can, lost here. Yeah, so these are the responses to that mode of variability. And so these are maps showing what happens when it's a positive factor, which corresponds to a low cold pool extent, like it's a warm year. In a warm year, pollock and cod are both further north, and that makes sense. In a warm year, arrowtooth is also further north, and the fall catcher processor fleet is further north, as are Aegzia pollock. And so, you know, essentially the story of this paper, skipping forward, is that in warm years, you know, a lot of stuff we care about in the Bering Sea all gets focused into this kind of similar spatial area. So during recent warm years or historical warm years, adult pollock overlap with Aegzia pollock that they cannibalize. Adult pollock are more overlapping with arrowtooth in warm years, which are their competitors. And there's a lower effort on average between bee season, fall fishing effort, and pollock in warm years. Yeah, so, and we can do these forecasts out. You know, in this paper, we did a decadal forecast. So, so that's sort of the, you know, kind of broad strokes structure of EOF, is to estimate one or more modes, one or more temporal indices, and then a spatial response to each of those indices for each variable. And that's sort of a sparse way of generating kind of ecosystem level dynamics. I should say that I toggled over, you know, I turned off my screen just to kind of give people a chance for questions here. I'll switch over to code if there's no questions. Okay. Well, let's see. So I've still got something running from last demo. Yeah, I'll just kill this because when people break out into groups, I've got some hints for how to make these models run faster. Let's see. So the final one. here is, I'll share my screen. So I'm just going to do the same thing. I'm going to make a new directory where I'm going to put stuff as we go, like what I kind of kick up right now. That's the new folder it'll go in. I've got a fresh R terminal, but I'm just going to set that as the working directory. And then I'm going to start just, copy pasting out of this EOF, empirical orthogonal function example application. That's example number 2. So in this case, I'm taking the 5-species ordination data set again, and I'm just running it with settings that looks like this. So there's some extra kind of options stuff that's changed between runs. OBS model has changed in ways that I'm not really going to get into. But as we started to talk about, the field config is sort of where the biggest decisions are being made. So in this case, I'm using a Poisson-linked delta model, which generates variation and encounter probability and positive catch rate using a single component. And so I'm turning off component 2 for some of these terms, except the beta term. And then I've got an IID variation for omega. So I'm going to have a separate spatial term for the first component for every species. I'm going to have a separate beta term, a temporal term for every species and every year. And then I'm going to have 2 factors for epsilon year. So there's going to be two modes of interannual variability being estimated, where the response of every species is independent. So there's no attempt to look at how similar species are, but they're all in terms of their response to those modes of variability, but it is estimating 2 modes of variability over time. And I'll just kind of kick this model off the same way as always, and then we can look at sort of what the output looks like. The same as always, it does this first kind of crunch to kind of make the extrapolation grid using a k-means algorithm that's described in detail, in the docs. The output, it only has a single linear predictor in this case, so it's showing this kind of ellipse, the distance at 10% correlation just for the first linear predictor. It has the same kind of extrapolation grid for the Eastern Bering Sea with these knots. It has the same kind of data availability because it's the same data set. And then let's see, these are the factor loadings. And so the first mode of variability looks like this. It's sort of a trend over time from negative to positive. And this is the response map for each species. And so I guess over time, there's been some change on average in Pollock distribution where they've had decreasing density. I don't know, maybe this is kind of west of Cod Alley. I don't exactly know. I mean, it's southeast of Pribilof Islands. I'm not sure what to call it. And over time, cod is decreasing in that kind of same area, whereas arrowtooth, yeah, interesting. So that anyway, I'm not gonna spend too much time trying to interpret this first factor, but I guess what it's saying is that over time, arrowtooth has gotten more high density in this kind of area that it's colonizing. And then the second mode of variability has this sort of oscillation and has a different set of response maps. So the second one, as it kind of turns out, similar to this is the terminal where I ran the model. I plot that mode of variability against the cold pool extent, by I, you know, without trying to do any real statistics about this, the cold pool extent is correlated with that second mode of variability. The correlation is 0.53. So it's not like astoundingly strong correlation, but you know, they both kind of generally have a low value in the early 2000s and an elevated value since then. So, you know, just using these 5 species, you don't get an astoundingly strong signal of the cold pool extent just popping out of the data the same way as we do with 14 species when we did the paper describing this. But, you know, it's also sort of a smaller demonstration for the sake of the, you know, quick code. So that's, again, kind of the whirlwind tour of what EOF might look like. And then, yeah, maybe I'll just try to show a little bit more about it. So this is sort of the spatial pattern that's generated for Pollock. So, you know, we can compare these across these examples. So in the index model, using the index model, we get this on the right, whereas using the EOF model, we get this on the left. And so, you know, I'd say the modes of variability, the 2 modes of variability being estimated in the index model on the left, kind of capture the pattern that in the, you know, 2009, say 2008, 9, 10, Pollock had sort of dropped, you know, lower densities in the northern portion of the Eastern Bering Sea, but also throughout the middle domain. And that's kind of a key feature of the dynamics of the stock. So that's being captured by the EOF model. But a lot of the other years are sort of, you know, the EOF model only has 2 axes to play with to generate changes in spatial configuration. And so a lot of these years in the kind of 90s and 2002, 3, 4 look kind of similar, even though the index model, the kind of more flexible model, captures interannual variability between those years that I don't really have any ecological story about, but I think we're probably a good description of their summer distribution. Yeah, and then these actually have the same data. So maybe I'll just kind of keep going on this, and anybody jump in if you want. The index, let's see, no, we can also, the JSDM and the EOF examples are fitting the exact same data set. And so you can actually look at AIC. So the JSDM is fitting 367 fixed effects. I wonder if one of these is using REML though. That might mess up the comparison. But the AIC for the JSDM is 388852. I think one of them is using REML. So actually, I don't think this will work the way that I'm looking at here. But yeah, yeah, I think I must have turned on REML for the EOF model. So the AIC is not going to be comparable between these 2 models without modifying it further. Anyway, so scratch that. But yeah, I don't know. Any questions with our kind of 4 minutes left in this slot before we take another break?
Hey, Jim, just because you mentioned it, could you define REML, please?
Yeah, sorry, that's, yeah. So like Alan Jur has a really good kind of cookbook for model selection for people that are interested in maximum likelihood versus restricted maximum likelihood, which is called REML. In a linear model, it's really easy to define REML, and it's the kind of, okay, so that I'm getting a little loopy right before the break, but the point of REML is that you get unbiased estimates of a variance. And so people might remember that If you take the mean of data, that's an unbiased estimate for the mean. And then if you take the standard deviation, you need to do that correction of 1 over n minus 1. You know, it's like the best estimate of the variance, you need to do that 1 over n minus 1 correction. And the same thing happens in a maximum likelihood model of any random effect variance, that the maximum likelihood estimate is not unbiased. It's biased in a very small way. And so REML is a way of getting an unbiased estimate of the variance of a random effect. And it's easy to, you know, it's feasible to do the math analytically in a linear model, but in these kind of big crazy models, it's not really possible to do by hand. And so the trick is that you can do REML for any nonlinear mixed effects model by just treating all of the non-variance fixed effects as if they were random effects. So it's telling TMB to treat a bunch of additional fixed effects as if they were random effects. And then you get unbiased estimates of your variances. So that's sort of the 2-minute version of kind of a bunch of kind of upper level stats. But the takeaway is that REML will be slightly better than maximum likelihood in terms of performance of your estimates.